So my name is Kyong Cho. I'm advised by Professor Kang Shin at the University of Michigan, and today I'll be talking about my paper entitled Viden, Attacker Identification on In-Vehicle Networks. So as I believe most of you may know, vehicles were composed of mechanical parts, but now they are being replaced with electronics. On top of that, actually, a lot of wireless connectivities are being added onto them. What this provides to the drivers or passengers are various types of friendly applications, but on the other hand, it also opened the remote access point to the in-vehicle network, which basically governs all the functions of maneuvering the vehicle. So obviously, from a security point of view, this is a security risk. So here is an example of a CAN bus. A CAN bus is the de facto standard for the in-vehicle network, where ECUs, basically computers in your car, are connected to each other and communicate in a broadcast manner. So there have been research that have shown that a compromised ECU can actually lead to, say, devastating results in like a crashed car, and even the Jeep was recalled because of these kind of issues. So against these attacks, there have also been a lot of research on the defense side. So basically, either building a new intrusion detection system, an IDS, or trying to build a new authentication scheme, which CAN bus lacks right now. They were trying to defend against these attacks. Especially for the IDS, there are a lot of efficient, effective IDSs out there. But the one main problem that is quite critical but remains unresolved up to now is they can actually detect the presence of the attack, meaning whether there is or not an attack on the bus. But one common problem they have is they cannot really identify who actually attacked it. So no matter how well an intrusion detection system actually detects the presence of the attack, if you cannot know the source of it, that would actually make the vehicle remain unsafe, and blindly treating all the ECUs as an attacker would lead to a very inefficient isolation or forensic. So in this talk and paper, we focused on how to identify the attacker ECU on the bus, which obviously provides a swift pathway, as I said, to isolation, forensic, and security patch. So in our system model, we considered an IDS, and also and on top of that, we also considered there would be a fingerprinting device which governs this attacker identification function. So the IDS detects the presence of an intrusion, and the fingerprinting device complements that by detecting where it came from. And against these kind of devices, we considered three different adversaries, all of them having this common goal of impersonation, meaning they might want to try to make the fingerprinting device believe that, say, the attacker is some arbitrary ECU, meaning some other ECU other than himself, or a specific targeted ECU. And depending on his knowledge or curiosity, the attacker can be just try to impersonate naively, which we refer to as a naive adversary. There has been work on how to fingerprint ECUs based on clock skew and timing, which was presented last year at Usenix. We consider an adversary trying to fool those kind of systems in terms, and we call them a timing-aware adversary, meaning they try to trick the timing and believe that the injection was made from some other ECU. We also finally consider an adversary called a timing voltage aware, which considers both timing and voltage and believe that either both or one of them would actually make the attacker be identified. So against these adversaries, we try to build a system called Viden, which is abbreviated from voltage-based attacker identification. Its goal is try to fingerprint ECUs, meaning computers on your car, based on measured voltages, without requiring any additional new information. So the main takeaway of our scheme is that we try to make it adaptable to various changes inside and outside the vehicle, such as temperature or a change in the status of the battery. And also we try to make it practical, not imposing any restrictions on what kind of message formats we might have to use or what kind of bus speed we have to use. We take all of that out and try to make this scheme to be implementable in, say, cars that you guys are driving right now. And lastly, but most importantly, we try to make this scheme very low cost. We tried to make Viden with a very low sampling rate because we didn't want to sacrifice the cost factor by increasing the sampling rate redundantly. So instead of using an oscilloscope, later we'll show we used a very small device to actually monitor the voltages and try to fingerprint ECUs based on that. So most of you would ask at this point why I use voltage. So before going into the details, I would like to give you some background on how CAN ECUs communicate with each other. So when CAN messages are basically a stream of bits of 0 and 1. And when they want to output a bit of 0 or a 1, they actually drive their two lines, CANH and CANL, to a certain voltage level. So by looking at the voltage level, other ECUs actually understand what kind of bits are being sent on the bus. So when some ECU is sending a 1 bit, it just makes both lines to be driven to 2.5 volts, which is just basically just being idle. And if it wants to send a 0 bit, it tries to drive those voltage lines to 3.5 volts and 1.5 volts respectively. But to actually output these kind of voltages, this is how a normal CAN ECU would look like. So there's a 5-volt voltage regulator trying to make that 5-volt voltage input for the microcontroller and the transceiver. And using that voltage, those are operated and then use those and to output the intended voltages. But the interesting fact we captured in achieving fingerprinting here is we try to look at variations that might occur from the regulator stage later to up until the actual CANH and CANL output. So because of process variations, the voltage regulators might not really output the exact 5 volts that they intend to. So this variation goes along until it reaches, say, the gate voltage gate of the CAN transceiver or the voltage input. And also, it's well known that there exists variation in the ground itself because a perfect ground is very difficult to achieve. So they try to achieve that mostly through a very small differential voltage. Because this variation just moves along and being affected by various process variations in the CAN ECUs, if you look at how the CAN transceiver looks like, because those variations are passed along to the input, the gate voltages, and the ground, and on top of that, because there exists process variation in those transistors, when an ECU, say, tries to send a 0 bit, there exists some variations in the actual CANH and CANL, which turns out to be quite unique per ECU. We don't really consider any measurements during when an ECU sends a 1 bit because that's basically a circuit that is turned off. So the most measurements were turned out to be quite similar between different ECUs. But when sending a 0 bit, we were able to capture those differences because of these variations. So as I've briefly explained, each ECU would have a certain voltage output behavior. And if it's different, the behavior turns out to be different. Then the question we try to answer is how we can actually capture such behaviors. So we actually captured those behaviors in 4 different phases. First, a phase called ACK Threshold Learning, which I'll elaborate in the following slides. So take this example of some ECU sending streams of 0 and 1 bits on the bus. So our Viden scheme, by looking at a certain measurement going over 2.75 volts, which means it's a 0 bit, it would actually know that someone is transmitting on the bus. It ignores any measurements from a 1 bit, and it continuously measures the voltage's output or as a 0 bit. And then it sees that that message has been collected in its buffer and refers those messages to that message ID. And because it's done, it tries to verify and fingerprint the ECUs. But the question we have to bring up here is, can we consider all these outputs to be, in fact, output by the actual transmitter? This was a funny fact that we find out during our research is that because of how the CAN frame format looks like, in fact, not all measurements are actually output by the transmitter. If it was, it would be far more easier. But because of this ACK slot, those voltage outputs weren't necessarily be output by the actual message transmitter. Why? Because in the CAN spec, they want in the all other ECUs other than the transmitter to actually output the voltage instead only during that ACK slot. So if say Viden, our proposed scheme, were to just blindly consider all these measurements as those output by the actual message transmitter, then it would be actually confused because in fact, out of the three, the last one was output by all other ECUs. So the first thing we try to do is how to distinguish this non-ACK voltage and ACK voltage. First, we exploit two facts that the probability of measuring this ACK voltage is not really high because there's only one bit within, say, about 128 bits of a CAN message. And the second property is there is a different voltage level for the ACK. Because those transceivers are connected to each other in a parallel manner, those voltage levels tend to be much higher in CANH and much lower in CANL. So we exploit this fact to actually derive two different things. Remember, because of the low probability characteristic, if we just out of say 50 measurements for that message ID, the mostly frequently measured voltage would mostly come from the non-ACK voltage. And if we were just always looking at the maximum value within say 50 measurements, we would sometimes get measurements from the non-ACK voltage, but as I said, with some probability, we would still measure the ACK voltage. So if you look at the kernel density of those most frequently measured voltage and the maximum voltage, this is how it looks. So by applying some stats, we derive the scheme and how to draw this line of determining whether this value would be a non-ACK voltage or an ACK voltage. So now we have those measurements only coming from the actual transmitter. We use those measurements now to actually fingerprint the ECUs. And we also found out that the distribution of the voltage outputs for different ECUs are quite different. So what we do is using those non-ACK voltages, we use, again, apply what the most frequently measured values were. And so also we look at the dispersions, say the lower percentile of CANL and the higher percentile of CANH. The reason why we don't look at the high percentile of CANL and the low percentile of CANH is because those values would have been output while they were trying to transit between a 0-bit transmission and a 1-bit transmission. So by looking at the dispersion of how their voltage are output, meaning looking at the distributions, we can actually figure out which ECU might have output these kind of messages. So then what we do is there might be some transient changes in those voltage measurements due to a sudden change in temperature or a sudden change in other factors. To eliminate that, we try to accumulate all those measurements from CANH and CANL both, and try to model that as in something called a cumulative voltage deviation. So because we're accumulating all those dispersions in CANH and CANL, what we can actually achieve is we can actually eliminate these transient behaviors that we had in our measurement process. And then eventually we can just look at those constant factors that are being output by those ECUs. So these you can see here the CANH outputs and the CANL outputs are mostly symmetric. This is because a CAN is a differential bus. So meaning if an increase happens on the CANH, there would definitely be a decrease on the CANL because of how they are designed in terms of circuit. So we exploit that fact to actually remove those transient factors and just try to capture those constant ones. Once we do this, what we can do is we can model them into a linear model, hopefully because we have captured those constant factors. And in the end, we get this kind of model here. Going through these processes that we've briefly explained, we can actually build a linear model for each ECU. and learn those on the fly using a very famous recursive least square algorithm. And finally, if we were to want to capture a certain attack and identify who actually attacked the bus, we can actually just collect those voltage measurements from those attacks and try to map those to one of the models that we had, which we will show later on how it showed. So by now using the voltage profiles, now we can identify who the attacker was. On top of that, we wanted to minimize the false positives and false negatives because in some corner cases that we encountered, there were some scenarios where this voltage profile, the timing voltage adversary might fool this Viden system. So what we also did was we not only looked at the linear model itself, but we also looked at the instantaneous values and tried to input those into a machine classifier. And then surprisingly, we also find out those machine classifiers can also be used in determining the source of the attack. So moving on to how we evaluated all these. As I said in the earlier introduction part, we wanted to build this Viden scheme with probably the lowest cost that we could have. So we built this Viden scheme on this Arduino board with a CAN shield on top of it, which approximately is like $50. And because higher voltage sampling rate would mostly relate to a higher cost, for example, if you think of a cost of an oscilloscope, we wanted to avoid that. So what we did is we connected the CANH and CANL pins to the CAN shield ADC pins, and by building a program that actually monitors those ADC pins, we were able to capture those voltage measurements, either coming out from some ECU on the car or in our prototype, which our prototype looked like this. So we configured 3 different nodes that are just programmed to just emulate some behavior of a ECU on the car, and also that V node, which is the Viden node, which has the ADC pins connected to the CANH and CANL, keep on monitoring the voltage outputs on the bus. So you can see that the CANH and CANL are also connected to a breadboard, which monitors all the outputs on that bus. Once we verified our results in a CAN-bus prototype, we also wanted to verify whether it actually works in the real vehicles. So what we did is we used 2 different vehicles, one a 2013 Honda Accord and a 2015 Chevrolet Trax. So to measure voltages outputs from those cars, we had to connect our Viden node to the OBD2 port, which provide that link to that CANH and CANL lines to the actual bus. And we also monitored and processed those measurements through our laptop. So in our CAN-bus prototype evaluation, we were able to verify that if the messages were sent by different ECUs, as you can show in this figure, the slope, which means the actual accumulated voltage deviation, will be actually different for different ECUs, meaning if we were to use this slope as some fingerprint, it can actually work. We also moved on to getting measurements from the car, and we obtained the ground truth from existing fingerprinting schemes, which try to fingerprint those based on timing. And with those ground truth, we also verified that voltage can be another thing that you can use to actually fingerprint ECUs, and in the end, identify the attackers. The same results were shown for a 2015 Chevrolet Trax, again showing the same slopes for those same ECUs, even despite those messages were having different ID values. So why this happened? We looked closely on those measurements. You can see here of an example from a Honda Accord that despite those ECUs are designed to and implemented to output always the 3.5 volts and the 1.5 volts on CANH and CANL, in fact, they weren't actually outputting the exact values. You can see here, like for different ECUs, the actual voltage outputs were slightly different. So this slight difference in the voltage outputs made us to successfully fingerprint those ECUs. The same things were shown on the Chevrolet Trax as well. And despite there were some transient changes in those measurements, as I said, we were able to eliminate those by accumulating all the CANH and CANL properties, and then exploiting that fact that CAN is a differential bus. Now this shows on a evaluation result that we had in our settings. So we tried to have one node to try to impersonate some other ECU by trying to carefully changing its timing and voltage outputs. But despite that fact, because we were continuously learning those voltage profiles, and Viden had a valid model of what that voltage profile might refer to, it was able to determine that the attacker is in fact Z, which was how it was meant to be. And lastly, we also evaluated various types of attacks in terms of timings and how it would behave in terms of how it would change the voltages or timings on 2 different cards. Mostly on one CAN network, there is said to be around, say, 5 to 15 ECUs on a one subnet. So for those subnet, we consider those number of ECUs and try to figure out what the false identification rate would be. And for those 2,000 different attacks, we find out the false identification rate was 0.2 to 0.3%. So to conclude the talk today, we talked about a scheme called Viden, which is a voltage-based attacker identification scheme. So it fingerprints the transmitters based on voltage measurements. It does not really fingerprint the transmitters based on others, because we found out voltage-based fingerprinting is the most effective one in terms of attacker identification. And for practicality issues, we did not really require any changes in the protocol or messages so that it can be deployed right now in passenger cars. And eventually, with all those, we were able to pinpoint the attacker ECU, and eventually, hopefully, this would actually provide a very swift pathway for isolation, forensic, and security patch for the OEMs. Thank you.
Hello, my name is Maria Mera from New York University. I was just wondering if you had considered how component aging would affect fingerprinting and the false ID rate.
Oh, yeah, that's a great question. So for our span of the research, we could not really look deeply into the aging issue, but of course that aging issue might affect the actual fingerprints. But that's one reason that we built our system to monitor all those fingerprints and rebuild those fingerprints on the fly. So I believe one interesting figure that you might be interested is we try to look at how those voltage profiles would change if you were to remodel them after, say, like 8 days or 10 days. And we found out, like you can see here, like we didn't really elaborate on the adjustment scheme, but before adjusting it, we found out the slope might change for all of those because of the battery issues. But we also proposed a scheme that can adjust all of them to those random changes. So hopefully, with those aging issues, we can also handle them.
Hi, Feng Wei Zhang from Wayne State University. So I'm just wondering, for your case, you only consider 0 bits. And so is that a limitation? Let's say if a message has a lot of, most of the cases, is ones. In that case, it's going to be, your scheme is going to be limited for those kind of detection?
Yeah, another great insight. So if it were to all have 1 bit, the lucky thing that we have here is like for every 5 consecutive 1 bits, the CAN protocol is always inserts a certain 0 bit after it. So it does not want any consecutive 1 bits more than 5 bits. So we will always have a 0 bit in our message. But as you said, if despite that stuffing, if the message was configured to always have a 1 bit, there will be less probability that we collect the data. But the CRC and those other fields that are fit to 0 bits, or those CRC fields, those are not really that the user can control. So maybe Viden would capture the measurements from those fields. Yeah.
Hi, I'm Mohammad Yasin from New York University. My question is that you're relying on the voltage variation, right? So the question is like, if as a circuit designer, so I do a if I can build a better voltage regulator, right, which smooths these variations, so then your security will be compromised. So does that mean that doing bad design helps the security?
Yes, so that's what I'm trying to bring up here. So I think basically, like even for the timing-based fingerprinting and also this voltage-based fingerprinting, those use process variations. So sometimes because of how the automotive industry is like works, because they have a lot of tier one suppliers in those, there would exist process variations, which hopefully for security point of view, it helps. So that could be a one message that we are trying to bring up here.
Yeah, great talk. So I was wondering if, let's say, your product becomes very successful, and I'm one of your like customers. How would I use this? Like, or how is it this envision? Is it like a sort of like in the Volkswagen case scenario that I put it as a test in the vehicle in a sequence of tests while I'm not operating, or would this be sort of like when I'm operating and then something like an ECU goes off and and then what to do afterwards, right? What would be
Yeah.
the
So ideally, would run with the IDS, like so because people, I believe automotive like OEMs are trying to implement IDSs on the car, and with those IDS, if you have just this simple function, you can not only detect the presence, but as soon as you detect an attack, you try to go through your models and like pinpoint at the attacker. Then that would actually tell what kind of say ECU to isolate or within that network. People are talking about that as well, or how to say if you want to shut down that specific ECU, you might want this kind of scheme. So it's like trying to narrow down all the say possible candidates of the attackers, and then helping those to actually deal with with their various means, I guess.
right, and that's what I was thinking. Like maybe the user scenario might be better for like a testing case, right? So the vehicle is not in real operation, but it's like undergoing some tests, like some facility,
Uh-huh.
and accelerate, decelerate, do anything, and then because when it's operational, I guess
Yes.
it's probably harder to figure out what to do when there's a malicious ECU, right? You cannot.
That's right. So I believe a lot of people are trying to figure out what also another research on what to do after detecting it, but we're trying to provide that link between what to do and whether.
Hi, nice talk. Given that the CAN bus is a shared medium, right? So what prevents the attacker to attack directly the IDS system, the IDS module?
Okay, can you rephrase?
So given that the CAN bus is a shared medium,
Uh-huh.
so what prevents the attacker from attacking the IDS itself?
So yes, so the IDS mostly operates by looking at the network traffic because messages are mostly deterministic, their timing. But of course, there are various ways that you can actually fool the IDS.
Yeah.
Which we also presented a paper last year that how to even detect that. But I believe, as you said, there could be more ways of trying to fool those IDSs. So that's why I think it's very important to look into various attack scenarios, because I think there would always come up a scenario that would actually bypass even the state-of-the-art IDSs for now. So yeah, there could be, but I cannot really say how for now. But there were some research on doing that.
All right, thanks.
Okay, so let's thank the speaker again. Thanks.
Thanks.